This is problem 42 from chapter 14. The Jeep has a weight of 2,500 pounds and an engine which transmits a power of 100 horsepower to all the wheels. Assuming the wheels do not slip on the ground, determine the angle theta of the largest incline the Jeep can climb at a constant speed of 30 feet per second. So, I'm going to use equation 1410, which says the power is equal to the force dotted with the velocity. They give me the power is 100 horsepower, and I want to convert that to foot-pounds per second, so I'm going to need to know that 1 horsepower is 550 foot-pounds per second, but I'll save that for later. No slipping means that you have a force of static friction. So if the wheels were slipping on the surface, you would have kinetic friction. We want to find this angle theta here, and we know that the velocity is constant, which means that the acceleration is 0. I need to draw a free body diagram for this situation. So if I look at the Jeep that I have here, I have a force of gravity acting downward, that's equal to m times g. I have a normal force which is perpendicular to the surface, and I have a force of static friction acting up the incline. Otherwise, the Jeep would be sliding down the incline. And I'm going to just treat the Jeep here like a point particle. It said you have a power transmitted to all of the wheels, but we're just going to treat the Jeep as a point particle there. So I want to do the force of static friction dotted with the velocity, but I do not know what the force of static friction is. So I have to use Newton's second law. I know the acceleration is equal to 0 because the velocity is constant. I have to break up the force of gravity into components. I know that this angle here is theta, which means that the angle that I have here would be theta also, which means that this angle here is theta. So I have the force of static friction pointing up the incline and then pointing down the incline. That would be the sine component, so that's mg sine theta. So the magnitude of the force of static friction is mg sine theta. Then when I put that in here, the force of static friction is pointing in the same direction as the velocity, so I get mg sine theta times my constant velocity. I know the power also, so now I can plug numbers in. So I have 1 horsepower is equal to m times g, which is 2,500 pounds, times sine theta times my velocity, which is 30 feet per second. So 2,500 times 30 gives me 75,000. So this is 75,000 foot-pounds per second times sine theta is equal to 1 horsepower, but the units don't cancel out the way things are now because I have 1 horsepower on one side of the equation and foot-pounds per second on the other side of the equation. It wasn't even 1 horsepower, it was 100 horsepower. Okay, but I know that 1 horsepower is equal to 550 foot-pounds per second, so 100 horsepower would be equal to 55000 foot-pounds per second, and now the units cancel out, and I can solve for theta. So sine theta is equal to, was that 55,000 divided by 75,000, and then I take the inverse sine, and I get theta is equal to 47.2 degrees. One interesting thing to note here before we move on is that we said we had to have a force of static friction acting up the incline, and I wasn't given the coefficient of static friction, but I could figure out the highest value that I would have to have for the coefficient of static friction, and I think it's worthwhile taking a look at that in this case. So we have the force of static friction acting up the incline, we already said we had mg sine theta acting down the incline, so this would be the cosine component, and then I have my normal force acting like this, and I know the maximum value for the force of static friction is equal to the coefficient of static friction times the normal force, and in this case, because there's no acceleration at all, the normal force is equal to mg cosine theta. So I have the maximum value for the force of static friction is equal to the coefficient of static friction times m times g times cosine theta. And we said there was no acceleration in this direction either, so I have the force of static friction, and then assuming it's at its maximum value, that would be equal to mg sine theta, but the maximum value for the force of static friction is equal to the coefficient of static friction times mg cosine theta. So then taking what we have here and solving for the coefficient of static friction, we have the coefficient of static friction is equal to sine theta divided by cosine theta, which would be tangent theta. Using the angle that we have here, that would be the coefficient of static friction is equal to the tangent of 47.2 degrees, and that gives us 1.0799, which is a bit of a problem. Have we ever encountered a coefficient of static friction which is greater than 1? Well, you probably didn't see anything like that in Physics 161, and although it isn't impossible, it's highly unlikely that the Jeep is going to have tires with a coefficient of friction greater than 1. So usually for car tires, the coefficient of static friction is about 0.7, maybe as high as 0.9, but it would be very unusual for car tires to have a coefficient of friction greater than 1. So, although we did get an answer of 47.2 degrees in this problem, I don't actually think in this case that the Jeep could be going that fast up an angle of 47.2 degrees without the wheels slipping. Oh, one other thing that we need to go back to here. So I said this was the maximum value for the force of static friction. So if you're not at the maximum value, then you would need an even higher value for the coefficient of static friction. So it only gets worse. So for this to work, you need your coefficient of static friction to be greater than or equal to 1.08.